Hello everyone, and welcome to the third Destination Space event in our series, Would We Lie to You About Space? My name is Helena and I'm an outreach officer for the Department of Physics, and I will be hosting today's event. You might have noticed from the title, but today's panel event is very loosely going to be based on the hit TV panel quiz show, Would I Lie to You? But obviously we are a physics department, so we are going to be putting a bit of a science spin on things. That being said, should say any and all similarities are purely coincidental. We're not making any money from this, and we just want to do some fun science, so please don't sue us. Great. Anyway, so if you're familiar with the TV show, you will also be aware that there is always some sort of comedy element to it as well. Now, as I've already said, we are a physics department and our panel is made up entirely of physicists, including myself. So we'll see how the comedy goes. We're going to try our best, but we'll see how it goes. Okay, so speaking of physicists, I think it's time for me to introduce the panel. So as I've already said, my name is Helena, and I'm an outreach officer for the department, which means that I enjoy sharing all of the science that we're doing as a department with an audience such as yourselves. And that also means that I get the pleasure of periodically attempting to drag various scientists out of their nice little science caves and make them actually talk to people about the work that they're doing. Shock horror, I know, and that's what we're going to be doing today. So moving on to the panel, we are joined today by 4 scientists, some of whom you might have already met in previous events in this series. Others you might meet again at future events if you want to come to more of these Destination Space talks. But today, everybody is gathered here in the same virtual room for your entertainment. So first up, we have someone who is both a self-proclaimed scientist and engineer. Now, famously, scientists try to understand the why behind things work, but they don't necessarily know how. Engineers, on the other hand, understand the how things work, but don't necessarily understand why. So here we have someone who combines both of those roles beautifully, in the sense that he generally has no idea why things work or how they work. So please welcome Dr. Tris Warren.
Thanks, Helena.
You're welcome. And I can see you're having fun with the thermal imaging camera there. Excellent. Okay, so next on our list of panelists, we have somebody who seems to have maybe become a bit too attached to the idea of a pet rock as a child. Now she seems to have taken that idea to a whole new level and is essentially a full-time space rock babysitter. So please welcome Dr. Helena Bates from the Natural History Museum in London. So just how many space rocks do you have to babysit?
About 5,000, so they're pretty unruly.
That's some serious parenting skills.
Yeah.
Excellent. Okay. So thirdly, we have another scientist who is also possibly a little bit too obsessed with rocks and is shortly set to publish some groundbreaking scientific results about how dark rocks actually look dark. Who knew? Please welcome Dr. Katherine Shirley. There we go.
Yeah, thanks.
You're welcome. I'm sure you'll get me back later for these not so subtle digs. Okay, and last but certainly not least, we have somebody who seems to be so sick and tired of being around people on our own planet that he spends all his time searching for other planets light years away from Earth. So please welcome Burtie Spry. Brilliant. So that is all of our panelists. So welcome everybody. Thank you for joining us and for being willing participants in this event. So let's get things going. Right. So on to the first round. So what we're going to do for this one is each of our 4 panelists are going to take it in turns to read out a statement about space. Now this statement might be true or it might be completely made up, and it's up to you at home as the audience to ask questions to our panelists to try and make up your mind whether you think it's true or if it's a lie. So don't be shy, and you can start typing questions as soon as we've read out the statement. And like I say, we'll clear questions after each one. After we've spent a bit of time interrogating the panelist who's read out the statement, we're going to do a short audience poll to see whether you think it's true or a lie, and then we're going to reveal the answer. Okay, so to get things started, we have Catherine. So would you like to read out your first statement there?
Sure. So our first statement is, we train astronauts in craters on Earth.
Okay, training astronauts in craters on Earth. So get typing any questions that you might have for Catherine about this. Yeah, okay, so one that I've seen a few times, why? Why do we do this? What's the point?
Yeah. So, well, there's lots of craters on the moon, and which we can see when we look at the moon. So we want to explore them on Earth so that astronauts are prepared when they get there.
Okay, so it's prepping for moon-like conditions.
Mm-hmm.
Which craters? Where are the craters on Earth? Where do we do this?
So the most popular one is called Barringer Crater. Meteor Crater is its more common name. It's in Arizona. And I think almost all the Apollo astronauts were trained there.
Nice, okay. So someone's asking, what benefits does training astronauts in this way have?
Well, so we want them to be able to find interesting and important rocks on the moon that will tell us about the moon's geology. So we have to explain geology to them on Earth so they know what to look for.
Okay. So, by the way, other panelists, if you want to jump in at any point and add to the interrogation, please feel free. Fun question here. Do the astronauts have to wear spacesuits while they're doing this training?
I think we're just teaching them geology. So for this part, we don't have to make them wear their spacesuits.
Okay.
And they're quite heavy as well. Though I have seen some more recent ones testing out some spacesuit prototypes out in the desert.
Okay. Another good question. Who is we in this statement?
Well, it's not me, not me personally, but NASA in general and other countries have their own space programs that train their astronauts. So I think a lot of them usually join forces.
Cool. Okay.
So if you've never done it in person, how do we know you're telling the truth?
I mean, that's the whole point, isn't it?
I've got friends, and there's definitely studies. And
You've got friends outside of this circle.
I know. I do have friends. And at Meteor Crater, there is a big cutout of an astronaut at the very middle of the crater that you can use the little like binoculars at the rim to find him.
So you've been to Meteor Crater, have you?
Yep.
Mm-hmm. Which one have you been to?
Me? You're not interrogating me.
No, it's not yet.
I've been to Meteor Crater or Barringer Crater, yes.
Are we sure it wasn't always just cutouts?
Yeah.
People are.
Nope, there are definitely real ones were there. Yeah.
Okay.
Yeah.
Right. Looking at more questions. So we seem to have answered quite a few. So there's an interesting one here. Would you include seas as craters?
I don't know that I would include seas, but interestingly, you can call the center of a volcano the crater of it. So we do train astronauts as well at volcanic areas because there's lots of volcanic areas on the moon as well. And so we want them to know all types of geology so they can look for different things that might be interesting to us to examine if they bring them back.
Okay. So a couple of final quick questions. Are robotics also tested at the craters? That's interesting.
Oh, that's a good question. I'm not positive about that, but I imagine they might try.
And quickly, how long does the training take and how much does it cost?
Oh, I do not know how much it costs, but I think they spend a few days to a week in each location. Some of them are harder to get to. So the Meteor Crater is privately owned, and you can go visit it. So it's kind of like a tourist spot. So that one's easy to get to, but some other craters, like some in Canada, are much more remote and difficult to get to. So that would take a while to get there and then learn about it.
Okay, so it's a big chunk of time and money that this probably takes up. Interesting. Okay, so like I say, we're going to be moving on quickly for these rounds so we get to everybody. So I think that's it for your interrogation, Catherine. So what I'm going to do is I'm going to launch a poll. And this should just pop up on your screens. You'll probably get used to this because we're going to do a lot of this. This should just pop up on your screens. And if you can click whether you think Catherine's statement is true or a lie. Okay, all right. I'm going to end the polling. Let's see whether people thought it was true or a lie. Okay, so the audience thinks that it is true. Shall we take a look at the answer? So in reveal, Catherine, do you want to read it out as I change the slide? So
Yes, it's true.
excellent. So well done to all those who said it was true. You have got 1 point. Excellent. Okay, so
And I
on
think we have
to...
a picture.
Oh yes, yes, we do have a quick picture.
Yeah.
So what's
That's
this?
the Behringer crater in Arizona.
This is the one you've been to
Yeah.
with the astronaut in the middle.
Yep.
What's the building on the outside of the rim? Is that a building?
Yeah, it's lucky that the crater landed there.
Yeah, just missed it, right?
Just missed it.
Yeah, that's the visitor center.
Brilliant. Okay, so next question. So we're over to Tris now. So we've got a bit of a picture around here. So do you want to read this out then, Tris?
Yep. So this image was one of the first images sent back from the Mars lander InSight. So this is an image from the surface of Mars. So InSight launched like 2 years ago, and it was a lander. So it just landed on the Martian surface, and it had a robotic arm on it that took instruments off the deck of the lander and then placed them onto the actual surface of Mars. So you can see in the foreground there one of the instrumentations, which was actually a seismometer. So it was measuring how much the Martian ground vibrated.
Okay. So what do we think, audience at home? Does this look like it could be one of the images, or do we think it's not? Right. Questions. Who launched this mission?
So it was a joint collaboration mission. It was a NASA mission launched from Vandenberg, which is in California. We actually went to see the launch. It was slightly disappointing because Vandenberg gets very foggy, and it also launched at 2 a.m. in the morning. So we all had to get up at 2 a.m., drive out to an old Air Force base, which was quite far away. And then we were all in a big field watching where the rocket would launch, except we couldn't see more than about a meter in front of us, and we were probably a mile or two away from the actual launch site. So we just heard the rocket go up. We couldn't actually see it.
Very
but yeah, it was a NASA mission.
NASA. Cool.
And joint with CNES, the French space agency, and the UK space agency.
Okay, cool. So we've got some people questioning the colors on the image. So why is there a sepia tint? Why isn't it properly red?
Yeah, well, that's just the color of Mars, slightly tinged red. Yeah.
Okay.
Most of the soil is red in nature.
Okay. How is the image quality so good?
Well, I mean, we're able to send pretty much the same sort of webcams you get in mobile phone technology up on these missions. This camera is actually an instrument deployment camera. It wasn't meant for any science, really. It's very similar to the sort of cameras you get in your mobile phone. It was just so that we could see, you know, that it was safe to drop the or to deploy the instruments onto the deck of onto the surface of Mars. So.
Okay. So some people seem to think that the rim of the image looks like a bit like a net. So can you explain that?
Yeah, I don't know what that is. Maybe it's just like a bit of rock or something. I think it might be where the like we're inside a bit of a crater. So there's like out to the edge. There's kind of we thought we landed in like a bowl-shaped crater that had infilled with dust, and I think you're just seeing exposed rock kind of out at the distance in the rim there.
Okay, interesting. What was InSight mission's objective? So tell us more about the mission.
Oh yeah, so the main mission objective was to listen to Mars quakes, so just like earthquakes but on Mars. And it actually did this. So we measured the first Mars quake. It would have been about a year or two ago now, probably about 6 months after it landed. We had a terrifying few months where we deployed the instruments onto the surface of Mars and then just waited for a Mars quake to come in and nothing for a few months. And then suddenly we got a nice big signal. So we were all happy.
Nice. Okay, when was this picture taken?
Well, I don't know the details. It would have been around, well, it's landed in November. It would have, first image would have come back probably a week or two after that. So let's say end of November time. On Mars, you call a day a sol, and sol 0 is when you land on the surface. So this would have been like sol, I don't know, 3 or 4. Well, actually, we've deployed an instrument onto the surface. So this might have been more like sol 60. So a few Martian days after it landed.
Okay. So some people seem to have noticed something by the rock in the top left. So can you tell us more about that?
Yeah, there's a little toy mascot. That was the what do we call that? We called that Bruce. Bruce was the mascot of the mission.
Was he really called Bruce?
Yeah, little Brucey there. I don't know actually what the cartoon character is. I don't recognize it.
Someone said
Maybe it was an
Marvin
American
the
thing.
Martian. Marvin the Martian, I think. Isn't it Looney Tunes?
No, it was Bruce the Martian. Bruce the Martian.
Oh, yeah.
We took him along on the mission on the deck, and then once we deployed the instrument, we used the robotic arm to pick it up off the deck and put it onto the surface.
See, we like to have fun as scientists as well.
Oh yeah.
Excellent. Okay, so just a couple more questions. How many instruments are there on this on InSight?
There were quite a few instruments actually. So there was the one you can see in the picture near Bruce the Martian, in the bottom right corner. That's the seismometer instrument. So there were 2 seismometers, one built in the UK, one built in France by the French Space Agency. And then there was another instrument called the Mole, that dug into the ground or tried to dig into the ground. That's not actually in this image, it's still on the deck. It's yet to be put on the surface. And then there was a whole suite of instruments for measuring the weather, monitoring the weather. So wind sensors, 2 wind sensors, a pressure sensor. What else is there on the weather? Wind, pressure. Oh, and temperature, and the air temperature.
Which leads nicely into one question we've got here. Was it hot or cold?
Well, it's the same as on Earth, right? So during the nighttime, it gets cold down to it's much colder on Mars at nighttime than on Earth. So it's like negative 60 degrees from the top of my head, and gets about 20-ish degrees, 10 degrees, something like that during midday. Okay. So it's just the same as on Earth, you get day-night cycles. This is obviously there for several days.
Cool. Okay, so I think
poor old Bruce.
Yeah, it's really
exposed to the elements.
Okay, so I think that's enough for your interrogation, Tris. Let us relaunch the poll and see what the audience thinks. So, do we think he's telling the truth, or do we think this is a lie? So, drum roll, the audience thinks that this is a lie by quite a significant majority there.
I was fooling no one then, was I?
So, what is the answer?
Yeah, that was a lie.
Okay, but
some of that was true.
Was it the nets or was it the toy? I wonder.
Yeah, bit of a giveaway there, wasn't it?
Good questions, everyone. Well spotted.
Yeah, good work on that.
Yeah. So I think we have a few. Do you have a few images that you wanted to share actually of this? Did you want to just quickly explain what they were?
Yeah. So just to explain how the photograph came about, really. The InSight was a real lander that landed on Mars about 2 years ago. It really did have all the instruments I described, but what you were seeing there were images from before we launched it, where we were testing it out on Earth at a NASA facility called the JPL. If you ever watch Big Bang, JPL's in that. That's where Howard works, the Jet Propulsion Laboratory. And so they were testing out operations for the mission. So we all kind of got in a room and we tried out different mission scenarios. And we had a Mars yard set up of what it might be like when we land on Mars, and they were testing out how to work the robot. And every now and again, people would go out and put little toys into the Mars testbed. So that's how the image came to be. So if you flick on to the next slide, Helena, there you are. You can see it in
the big reveal.
Was he really called Bruce?
No, the PI of the mission is called Bruce. That's why I use that one.
I can see there's a TARDIS down there. I like that.
Yes, and they moved them every day, so it looked like they were moving around on the surface. Because we were in another room getting all these images back as if it really was on Mars. It was quite entertaining.
Yeah.
And I think the final slide, there you are. That is it really on Mars this time. There's no aliens or weird nettings in the background.
So
That's still quite red though.
Yeah, the
so
colours
Mars
are
really
quite
is red.
similar. Yeah. Great. So well done, everybody who managed to figure out that was just a barefaced lie. But that's what we're doing today. We've got some truths, we've got some lies. Okay, so next we have Helena Bates. It's very confusing saying my own name to somebody else.
I
Anyway.
know. Thank you, Helena.
Sorry.
Thank you.
So do you want to read out your statement here?
Sure. So my statement is the Japanese landed a rover on the surface of a 1 kilometer diameter diamond-shaped asteroid, which had the ability to hop around on the surface a few times, but unfortunately it landed upside down.
So we've got an upside down landing rover.
Yes. Yeah, so
That
this
must
is,
have been-
yeah, this is a mission that was launched in 2014 by the Japanese Space Agency, and it's called Hayabusa 2. And Hayabusa 2 is a really special mission because it's what we call a sample return mission. So it's traveling to a body and it's going to pick up samples and bring them back. So a little bit like what the Apollo missions and the astronauts did on the moon, but this is obviously without astronauts. So it went to an asteroid that's kind of floating around in space that's only about 1 kilometer in diameter. And they also had a bunch of little rovers that they deposited on the surface. And the main rover that they had was called Mascot, and Mascot had the ability to kind of hop around a little bit, but when they put it down, it kind of tumbled down and accidentally landed upside down.
That's so disappointing.
Yes, it was a bit sad, yeah.
Yeah.
They did manage to, because it has that ability to hop, they did manage eventually to flip it back over again, but initially it was a bit disappointing, yeah.
Okay.
Did they take a mission mascot with them, or?
Oh no, the thing was called Mascot, so they didn't need to take any more mascots with them.
It was his own mascot. Excellent. So let's get to some questions. What was the name of the asteroid? Did it have a name?
It did have a name. It was called Ryugu, which is a Japanese like river deity, I think.
Nice. And what was the nature of the asteroid? Like, why were we interested?
Oh, okay. So, well, very interesting. So the asteroid that we went to looks as though at some point in its like history, and its very, very old history, it might have had water on it. So it doesn't have water on it anymore, but when we look at the rocks and minerals that make up the asteroid, they look like clays, basically. So like the sort of thing that we find in the bottom of rivers and where there's been water previously. And so we wanted to go to kind of just investigate whether there was water present, like when that water might have been present, how much water was present, because water is really important in our solar system as a whole. So it's interesting to find out.
So that's the why they wanted to land it.
Yes.
Whereabouts is this asteroid?
So it's a near-Earth asteroid. So most asteroids are located between Mars and Jupiter, but this Ryugu is in a near-Earth space. So it orbits on an orbit relatively similar to Earth, but different enough not to be worried about it, if you know what I mean. Like it's not going to impact us or anything. Currently, it's actually quite close to Earth, I think, because Hayabusa 2 actually returned to Earth. You know how I said it was sample return, it actually brought its sample back, and that arrived back in December. So yeah.
So you've actually got some space rocks from this.
Yes, we do.
Your favourite thing.
My favourite thing.
Excellent. So we've got lots of people asking, I think, final question, how and why was it jumping?
Okay, so the way that the thing is designed is it basically has like a little lever thing that it can like push out that kind of pushes it, and so it doesn't like move necessarily, it just kind of flops. technical term there. It like
Absolutely.
flops from one place to the other, and they wanted to do that just so that they could sample multiple areas on the surface of this asteroid to try and get the maximum amount of science.
So that was the way it moved. It just kind of like flopped around like fish.
Yeah, a little bit. Yeah.
Interesting method of moving. Okay, cool. So I think we'll end there with your interrogation there. So let's launch the poll for this one. Do we think Helena is telling the truth about this upside down rover, or do we think it's a lie? It would be so disappointing if you spent all this time on a mission, planning, launching, and then you get there and it just kind of like lands.
Yeah, it would be.
At least you got some space rocks from it.
Yes, we did. We also got a bunch of other like science from it as well. So it's not,
great.
you know,
Bonus science. We
bonus
like
science.
So I can reveal that the audience thinks you are telling the truth, although only by kind of a slim margin. So not as wide a margin as the last one.
Those that are lying, why do you think I lied? That's what I want to know.
Interesting. Pop your thoughts in the comments, in the chat rather. Okay, so let's see. Let's reveal the answers. So Helena, what is the answer?
It's true.
So this actually happened.
It did actually happen. Mascot, the mobile asteroid surface scout. It landed upside down, and then they did manage to hop it over again. So it did manage to get some data, which is good. But little mascot.
Okay, excellent. Right, so final question in this round, final statement. We are over to Burtie. Okay, so Burtie, would you like to read out your statement?
We are planning to visit an exoplanet by the end of this decade. So an exoplanet is a planet outside of our solar system, and we're going to send a probe to go and visit it. So at the moment we can only really see it, see exoplanets from afar. At the end of this decade, we're actually going to go up close and have a more in-depth look into one of them.
Yeah, people want to know like how far away are we going with this, and what's the mission called?
So we're going to go to Proxima Centauri B. So Proxima Centauri is the closest star to us, and Proxima Centauri B is the close-in planet near to the star. It's called the Michael Dider mission, which is after two of the scientists that discovered the first exoplanet back in 1995. So what was the other question? Was that
like how far away is it? How long will it take to get there? That seems to be a common theme.
So it's 4.2 light years away. So it's going to take, but we're going to develop some. We've got the technology we need to get there. So we're going to travel incredibly close to the speed of light, and so it'll take around 4 years to get there.
Okay, so that would be a long mission. Okay, yeah, who is we? Again, we've got that question. So who's planning this mission?
So it's an international collaboration. So both NASA and ESA are working on this, along with other space agencies. Nice.
There's a lot of international collaborations when it comes to this. Excellent.
ESA, the European Space Agency, right?
Yes.
I forget, we use so many acronyms as scientists. We have to explain what we're actually talking about. Good point. What problems could the rover come into while going to the exoplanets? So what problems could arise?
Well, there's going to be two parts to the mission. So we're going to have an orbiter and a probe that's going to land on the surface. So hopefully we don't encounter the problem that Helena faced with landing upside down. So I hope it's a slightly smooth landing there.
I hate to say it's not even the first time that it's happened that something's like landed upside down on a body. So yeah, best of luck.
Okay. And yeah, I saw someone asking, so yeah, what do you think the success rate would be of the mission? So given that there's all these problems, how successful do you reckon it would be?
I'd give it maybe 50-50 odds. And it's the first time we've done something outside of our solar system, so there's all sorts of risks there. We're slightly better than that for missions within our solar system, but yeah, landings especially are hard. But we still have the orbiter, right? So even if we have a problem with the lander, then we'll still get some valuable up close data. like we can actually directly image the planet. At the moment, we can't actually see what the 3D structure of it really is with a sort of direct image. Anyway.
Cool. So what kind of fuel would you use for this, and what would the propulsion mechanism be? I feel like they're kind of similar questions.
So they're going to use a light sail, so a really essentially giant mirror, and they're going to shoot it with a really powerful laser beam from Earth. And the energy from the laser is going to push the spacecraft, to the speeds that we need to get there.
That sounds like something out of science fiction. That sounds really cool. Okay. Right, so yeah, we've got the technology. So that's the how. We've said how far it'll be. Yeah. How much will this cost? This sounds like it's going to be a big endeavor.
It will be a big endeavor. I don't have the number off the top of my head, but I'm going to assume probably going into sort of the billions, I would have thought. Low billions.
So this is going to be a big one. It's going to be a long mission. It's going to be far away. We could get some cool data from this though. Okay, so I think that seems to be the general trend with all the questions. So I think we will launch our poll for Burtie's statement here. So what do we think? Do we think we're going to go to an exoplanet by the end of this decade, or not? What do we think? So I can reveal that the audience thinks that you are lying by quite a strong margin. Not very convincing. Okay, let's.
It is, in fact.
Hang on. Yep.
Like...
It is a lie. Yeah, it does sound very like. I mean, I said that science fiction-y, but yeah. So is that technology that we could actually use, or is that just kind of made up?
So some of the ideas are things that people are starting to think about. It's not something that's really going to happen soon. But the idea of a light sail is, if we were to do something like this, it would have to be incredibly small. So the whole spacecraft would have to weigh sort of grams, and it'd be an incredibly lightweight mission. And the idea of a solar sail is possible, and people are thinking about it, but there's a lot of technological development that would have to happen before we could do anything like that.
Great. So possibly a prospect for some of you budding scientists at home to begin working on in the years to come. Excellent. So let's move on to round 2. So we like our pictures, we like our figures, we like our graphs as scientists. So what we're going to do for this round is we're going to have our version of a picture round. So what we're going to do is we're going to split the panel into 2 teams of 2. So we're going to have Helena and Catherine joining together as the sort of rock lovers, geologists, and then we're going to have Burtie and Tris joining together. And what we're going to do is each team is going to present a plot, which means like a graph or an image that they have made, but it's only going to have been made by one of them. But each of them are going to try and convince you at home that they're the ones who've made the plot. Okay, so we're going to do something similar. We're going to show the plot, we're going to have a little bit of discussion about it, and then we're going to have a vote on whose plot you think it is, and then we're going to reveal whose plot it was and what it actually is. Okay, so first up we have Helena and Catherine with this, what seems like a bunch of squiggly lines. I mean, that's a lot of graphs in science, isn't it, really? So who wants to go first? Should we start with Helena? So what is this graph? Very, very quickly, like 30 seconds.
Okay.
What is this graph?
So this is actually thinking back to what I was talking about before with Hayabusa 2. So you all know I'm telling the truth. This is a few cross sections of the topography of craters on Ryugu. So as you go from left to right, you're basically traversing a crater, and the height of the graph is showing you the kind of shapes and structures that are inside the crater. And it looks a little bit different from what we know associated with craters on Earth, because Ryugu is very small and its gravity is very weak. So the asteroid actually, or the impactor actually doesn't really create that really nice, simple bowl-shaped craters that we're used to. It produces this really complicated structure. And the different lines here just represent different craters that we've investigated. So the dark black one is actually quite an unusual one. So that's one.
Okay, so that's what Helena says. What about Catherine?
So this is actually a plot of emissivity spectra, which is basically a mineral's fingerprint and the energy that it's giving off. So what I wanted to do was I did an experiment looking at the same type of mineral, but at different sizes. So if it was a rock or like sand size or like dust size, to see if it still had the same fingerprint, basically. So that's what the different lines actually are. They're different sizes of the same material to compare how different they look.
I don't believe you.
Okay, so get asking your questions, everybody, to try and decide whose plot it is. So we've either got Helena's cross-section of a crater, or we've got Catherine's mineral fingerprint. Okay, so good question here, and I will present this to both of you. What are the labels of the axes? So we've obviously removed them to create an air of mystery, but what are the labels for your graph?
So for me, it's, well, it is height and length.
And it's actually emissivity on the Y and wavelength on the X.
So what do you mean by emissivity? What does that mean?
Yeah, that's energy emitted from the material.
Okay.
Seems a bit complicated, doesn't it, really?
So yeah, we've got several people asking like, what is a mineral fingerprint? So can you tell us just a little bit more about that?
Yeah, so basically minerals will emit energy at certain wavelengths depending on the atoms and the structure of those atoms that are within that mineral. This is an olivine. So at so like this big part in the middle that's kind of got like 2 or 3 little squiggles, basically, that's telling you that the silicon and oxygen atoms are moving around in a certain way based on the structure of the mineral.
Okay, great. So back to Helena and the crater. So got someone asking, if it was a crater, how did it make that shape? So why is it that shape?
Well, so basically what happened for the lighter colored lines, what you had here is some sort of iron metallic object impacting into the surface. So the other thing you have to know is that this is vertically and horizontally like exaggerated. So actually, if you looked at the crater, it wouldn't be this obvious, but we do that a lot with quite a lot, like crater plots, even on Earth and things like this.
How much did you exaggerate, Helena?
How much did I exaggerate? So this is about 10 times exaggerated. So it like, if you do look, I will admit they don't look this exciting when you actually see them on the surface. But the other thing this is telling you is these are angled impactors, which is why you have quite a lot of ejector blanket on the left and less on the right. Yeah, but yeah, and then the black line we think is actually like rather than a metallic impactor, we think that that is a rocky impactor, so it probably broke up a little bit more, which is why you have this divot where the others don't.
Okay. So for both of you, how long did it take you to record this information, and how did you take these measurements? So tell us a bit about how this was made.
Well, it was made using the LiDAR instrument on board Hayabusa 2, which basically is a laser that measures the height of various things. Quite a quick measurement. They just, when the spacecraft is over the surface of the crater, it just kind of pings a laser down, records how long it takes for that light to reflect back, and then it gets an idea of height, relative height. So really quick. I'm afraid to say I didn't collect the data. The instrument collected the data, so.
Well, I actually collected this data in the lab, and it only took a couple hours to heat up all the minerals so that we could get their energy signatures.
Okay, so I think we will stop there and we will do our poll. So whose plot do we think this is? Do we think it's Catherine's, or do we think it's Helena's? So have a go.
I can't vote. I can't vote for myself.
No, you can't vote for yourself. That's kind of defeats the point here. Just like you couldn't vote for the right answer.
Would you vote for yourself, Helena?
Yeah. Obviously, because I'm right.
Okay. So I can reveal that the audience thinks that this plot is Catherine's. But there was a decent chunk of people who thought it was Helena's. Okay. So
I'm really upset.
People think you're lying. Okay, so we can reveal that this plot is, in fact, Catherine's. So well done to you at home if you got the answer right. And this is what it looks like in full with the axes labeled and all the other little details on it as well. So well done if you got that at home. Catherine, did you want to just say anything else very, very briefly about this, or is it just kind of self-explanatory now?
I mean, I explained most of those things, I think.
How did you publish it in the paper? Did you put the axes in, or did you do the original?
Yeah, I made people guess in the paper.
That's how scientific papers work, right? Just
Yeah.
Nice.
Okay, so on to the next team. So let's have a look at Burtie and Triss's plot. So here we have an image. So we've had a graph, and now we have an image. So let's decide whose plot this is. So Burtie, do you want to tell us about your plot here?
So this is a temperature map of an exoplanet called WASP-43b. And WASP-43b, it's a Jupiter-sized planet, but it's on an orbit much, much closer to its host star. So it's incredibly hot. What you're seeing here is, so it's a temperature map. So you're seeing the various thermal structure across the surface of the exoplanet.
Okay, so we've got a temperature map of an exoplanet. Triss,
But
what is your
like
plot?
his exoplanets. This isn't an exoplanet. This is actually the moon, much closer to home. And what you're seeing is a temperature plot, or it's a derived temperature plot. So it's actually, the color is showing you something called thermal inertia, which is a parameter that describes how quickly or slowly a surface heats up. Its resistance to heating is what's really being shown here. And you can see craters coming up in the data. You can also see that as you go to the poles, you're getting to a different color. That's not actually because the surface is changing. What's happening there is the model itself is actually breaking down. The model I'm using to derive the thermal inertia value, the model doesn't work up at the poles because you get weird shadowing and scattering going on. Yeah.
Okay, so temperature plots, one from the moon or one from an exoplanet. Okay, so let's get asking questions. So quick one to start off. Why is it that shape? Why is it like oval shape?
Moon's flat. No, it's just so you can see the whole surface. So I've spread it out so you can see right across the entire surface. It's quite difficult representing a sphere on a flat surface. There's many ways you can unravel it, but if you kind of imagine it trying to unravel it, it doesn't unravel very well. You have to make some areas smaller or larger. There's a whole talk we could do on that.
I mean, it's like when you see a map of the Earth, isn't it? It's that sphere kind of rolled out in a flat representation. Okay, so question to both of you then. How did you get the picture? So
this picture is, so it's not an image in a conventional sense, right? So it's not something we can just take with a camera. It's a reconstruction based on looking at the exoplanet for a large amount of time. So to use an analogy of the moon here, actually. So when you look at the moon, you see the different phases of the moon, right? So you have a full moon, you have a new moon, you have half moons, crescent moons, etc. And when you look at it in those different time periods, you see more or less light coming from it, right? So it's bright as a full moon and very dark as a new moon. And we can do the same thing with exoplanets. So we can have a look at how much light comes off the exoplanet at different parts of its orbit. And from that, by working out how much light we see, we can work out the temperature map. So it's reconstructed from looking at the exoplanet over a large amount of time.
okay, so it's not direct temperature measurements because you'd probably need some sort of probe or something to do that. It's inferred from light. Okay, interesting. Triss, how about you? What do you have to say for yourself?
So Bertie, this wasn't from your made-up mission earlier then? This isn't data returned from that?
No.
All right. No, this is so this was a mission to the moon called well, the instrument was called Diviner. It was a NASA mission called Lunar Reconnaissance Orbiter. It's been in orbit around the moon since 2010, and I take the temperature measurements it makes of the surface, and it's got temperature measurements at lots of different times of day, so I can watch it cooling to nighttime, the surface, and then I use how fast it cools to nighttime to make this plot, which tells me the resistance of heating, or the resistance of heating and cooling at every point on the surface.
Okay, So we've got several people questioning you, Burtie, about how we've managed to get data this good for an exoplanet. So do you have anything to say to that?
Well, it's you can get really good data if you just observe for a really long period of time. So this was constructed over hundreds of orbits of this single exoplanet. This was not just a so it takes a lot of time and a lot of time, and it has to be taken from missions in space. Right, so this is taken using Hubble Space Telescope, and observing hundreds of orbits and then stacking all of that data together to produce this image.
Does that mean like 100 years?
100 years of that exoplanet.
Okay, so how long is the orbit of
the... incredibly close in, so its orbits, yeah, its orbit's only a few days. So it, yes, so you can get many orbits relatively quickly.
Okay, so different imaging techniques. Right, yeah, so we've got some people asking about the colors being used. So why is it blue and not red? So quick answer about the scale here. Again, we've taken off the labels, but yeah, who can explain the colors for their plot?
It's just the colors that I picked when I plotted it. They're not real colors. So I just chose blue to be a low end of the scale and yellow to be the top end of the scale. There's lots of different scale colors you can use. I like this one. I'm red colorblind, so I can't see red.
Yeah, you could use rainbows or anything. It's just an arbitrary color. Okay, so just looked at the time. Let us go to the poll for this one. So let me launch the right one. So who do we think this plot belongs to? Do we think it's Burtie's or do we think it's Triss's? So I can reveal that the audience thinks that this plot belongs to Triss. So well done, Triss, you were very convincing. So let's see whether that is true. So I can reveal that the plot does in fact belong to Triss. You were right. Well done at home. Brilliant. So this is what the plot looks like in full. Triss, do you have anything else you want to very quickly say about this before we move on?
Nah, just move on. It's
okay,
as I described earlier.
Clearly. And Burtie, did you want to say, I think you wanted to say something about this. So part of your explanation wasn't a complete lie. You weren't completely lying.
Yeah, so this is actually so the images on the bottom are a real temperature map for WASP 43b, and we can in fact measure it by observing the exoplanet at lots of different phases. So that method is used, and yeah, that's what you see here.
So you were telling the truth, just not about that specific picture.
Yes.
Excellent. So we can get data from exoplanets. Nice. Okay, so very, very quickly, we are going to move on to round 3, our quick fire round. Okay, so we're going to go as fast as we can on this. So the idea here is we have 10 very short statements about space. And what we're going to do is we're going to read out a statement, instantly give you a poll in the audience for you to decide whether it is a fact or in fact a science fiction. So either true as a fact or false as a fiction. And then we're going to have whoever's statement it was just describe it very briefly and tell you a little bit more about it. Okay, so first one, we have the Earth is a perfect sphere. So what do we think on that one? Let me get the right poll up. So do we think this is a fact or fiction? So the audience have decided that this is fiction. Okay, so I can reveal that this is, in fact, a fiction. Well done, you got that right. So who wants to say a little bit about the fact that the Earth isn't a perfect sphere?
Yeah, well done if you got that right. It's not a perfect sphere. It bulges at the center and it's thinner up at the poles.
I thought it was flat.
It's not flat. It's nearly a sphere.
Really not.
And then obviously you have slight local undulations as well.
Yeah, so it's not an exact sphere. Brilliant. Okay, so statement number 2. A comet from another solar system has passed through our own solar system. Okay, so let's see what people think. Do we think this is fact or fiction? Okay, so the audience have decided that this is a fact. So by quite a strong margin. So I can reveal that this is indeed a fact. You're doing brilliantly at home. Well done. I think you've got all of them correct so far.
Got a smart audience.
Very smart audience. So, Helena, I believe you wanted to say a little bit about this one.
So in 2017, there was an asteroid that we call Oumuamua that we basically only detected.
What was that? What was
Yeah,
the
what
name
did
of
you
that?
Oumuamua.
How long have you spent
It's a-
practicing that?
It's basically it was because it was discovered using the telescope facility in Hawaii, so it was named after a Hawaiian term. We only really discovered it as it was leaving. It seemed to come in. So everything in the solar system exists in a kind of flat plane, but this thing was coming in at an angle, and it was this weird cigar-shaped body, and we basically only really detected it as it was traveling out really, really, really fast. So the hypothesis is that it comes from outside the solar system. Pretty
Nice.
cool.
Nice. Okay, so next one, we'll get through a few more, I think. We are able to tell what exoplanets are made of. So this is a little bit more split than the others, but we still think that this is fact. So we think we can tell what exoplanets are made of. So let me stop sharing that and reveal that you are correct. This is indeed a fact.
Finally,
So-
something real about exoplanets.
Yeah, something real. We're not having to lie about exoplanets. So Burtie, do you want to tell us something about this?
Yeah, so we can. So using a method called the transit method, where the planet passes in front of the star, we can look at the shadow the planet creates, and we can, from the properties of the shadow, we can infer various properties about the exoplanet. And yeah, if you want to hear more about that, come to my talk soon.
Nice plug. So Bertie's giving a talk in 2 weeks, all about exoplanets. And if you're more interested in space rocks, Helena's giving a talk next week. Next one. So the biggest volcano in the solar system is Helena Cotterill. I have no idea if I'm pronouncing these right, by the way. On Jupiter's moon, Io. Okay, so what do we think? Do we think this is a fact or a fiction? Interesting. So the majority think that this is fiction, so this is false, but there is a decent chunk of people who thought it was true. Okay, so I can reveal that this one is, in fact, fiction. So this is not true. So Catherine, did you want to say a little bit about this one?
Right, it's a fiction. I think people in the chat are saying yes. On Mars, Olympus Mons is the largest known volcano in our solar
Bertie has
system.
climbed that one, so.
Yeah.
Yeah,
But
so I think-
Io is
Poor
actually
Bertie.
one of the most volcanically active places in our solar system. And I
Yeah.
think, Helena, you have some picture. Yeah, so you can see that's a volcano erupting from on Io. And I think you also have the picture of Olympus Mons,
Yes.
which is like the size of France, basically.
Wow.
And it's very huge, but it's also like so large, and the slope is so shallow that like you wouldn't really know that you're on a mountain if you're on it, which is kind of crazy.
Right. Okay, so next statement. So this is a fun one. We discovered a fossilized bacteria in a Martian meteorite. So a fossilized bacteria. That definitely sounds interesting. Okay, so what do we think? Fact or fiction? This is really interesting. So this is very split. So slight majority think that this is a fact, but it's very split. Okay, so fun reveal. I can reveal that this is, in fact, fiction.
Fiction.
So
Obviously, this
not-
is one of my ones. 'Cause
Yeah.
Space
Well,
rocks.
judging by the cackle that you gave when I was reading it out, it was kind of obvious. Space rocks. Okay, take it away, other Helena.
So in the 90s, scientists discovered what they thought was a fossilized bacteria in a Martian meteorite. And I think we do have a picture of it.
Yes.
So they found this and they thought, oh, look, it's a fossil of a bacteria. And in fact, I was looking this up earlier today. They've never actually officially disproved that it isn't a fossil. What they have said is that it's not enough. Just the shape of it doesn't dictate that it is a fossil. So they're basically saying it's not a fossil. So it's a kind of fact/fiction, but it's pretty fictional. So we actually have a picture of this up in the Meteorite collection because we like to look at it and laugh.
Excellent. Okay, next. The only country to have 100% success record of launching rockets into space is the UK. Okay, so again, very split, but a slight majority think that this is fiction, that this is false. Okay, so I can reveal that this is, in fact, a fact. This is true. Okay, Tris, did you have something you wanted to say about this one?
Yeah, it's just a quirky fact. The UK has actually only ever launched one mission. It was just a low Earth orbiter into space. It was called the Black Arrows. That was the name of the project. And just before they launched the rocket, their funding got cut, but they launched the rocket anyway. And so we've only ever launched one rocket into space to date, and it was a success.
I mean, one success.
All the other countries have had unsuccessful launches, right?
Yeah, normally it's about 50% success rate. Rockets are pretty, notoriously dangerous to launch into space.
I mean, that's statistics for you. If you only launch one and it's successful, 100% success rate, best in the world. Brilliant. Okay, let's move on very quickly. Ooh, clicking on the wrong thing. Right. Titan, which is a moon of Saturn, has a water cycle. What do we think? A water cycle on a moon.
Ooh.
This is the most split. I don't think there's a majority here. I mean, if you want to take it as a majority, think that this is fiction, but I'd say that's very evenly split. So what is the answer? Let's have a look. So the answer is in fact fiction. So there isn't a water cycle on this moon, but Catherine, you did want to say something about this.
So it's not with water, but it is very similar to the water cycle on Earth, but it's with ethane and methane. And they do have, there's lakes of it and a big atmosphere, and it can rain and everything. So it's pretty cool. I think you have a picture of that we have of it. You can see the kind of the clouds. It's not as high resolution as we have of the moon, but you can kind of see.
That's so cool.
There is a cycle, but it's just not a water cycle. Interesting. Right. Okay. Last few ones now, I think. So the planets in our solar system formed roughly where they are seen today, and they haven't moved since. So since they were formed, they've just kind of stayed roughly where they are in our solar system. So what do we think? Do we think that's fact, or do we think that's fiction? So we're back to a majority rule here. The majority rule thinks that this is fiction, that this is false. Okay. So let's see. I can reveal that this is indeed fiction. So that is not true. So who wanted to say something about that? Was it Tris again?
Yeah, I can say something. So well done if you got that right. So most of the planets, well, the current thinking is that most of the planets formed in possibly different locations to where they are today. And then there's a theory called the Grand Tack, which is that Jupiter actually moved in after it formed, moved in closer to the sun, sent the whole solar system into something called a resonance, shot out a whole bunch of material out of the solar system, kind of all just went crazy. And then it kind of tacked back and went back to the location we see it today. There's also all sorts of other theories as to we could have had more planets than we see today, and one of them actually got ejected from the solar system in that theory. So yeah, well done. Planets move around.
They do indeed move around. Okay, I think there's just a couple more and then we're done. So we expect there to be at least one exoplanet for every star in the universe. So one exoplanet for every single star. That's a lot of stars and a lot of exoplanets. So what do we think? Do we think this is a fact, or do we think this is a fiction?
Burtie, I did see there was a question on what is an exoplanet. Do you want to give a quick explanation as well?
Oh yeah, so an exoplanet is any planet that's outside of our solar system. So just a planet around a star other than our sun.
But you know how like in our solar system, the like rules for being a planet are quite strict. Like, can they constrain that enough to actually say it's a planet and not a dwarf planet?
Well, we can. We're primarily. It's really easy to detect big planets. We're not currently at a point where we're detecting these really small things that we're not sure if they're a planet or an asteroid or these kind of things. So we're not yet worried about the small things. We're not quite there yet. Maybe that might be a problem soon. We have detected an exocomet, but I don't think anything else.
Interesting. So let me share the results on this one, because they're again very split indeed. But slight majority on fact. So I will stop sharing that, and let's reveal that this is indeed fact. So that is a lot of potential exoplanets. So Burtie, did you want to say anything else very quickly about this?
No, yeah, just a lot of exoplanets in the universe. So possible implications for other civilizations out there. Just a lot of planets. So we're definitely not in a minority in that we have multiple planets around this stuff.
Excellent. Okay, so I think we're on the final one now. We are landing on Mars tomorrow. Obviously not us personally, we are, you know, firmly in our houses.
We're coming to you from a spaceship.
Yeah.
But
I
just,
don't know about you, Helena, but
oh well, I mean, I'm only speaking for myself here. But we, as in the sort of royal we, someone is landing on Mars tomorrow. So what do we think? Is this fact or fiction? So slight majority again think that this is fact. Okay, so let's stop sharing the results, and for the final reveal, this is a fact. There is something landing on Mars tomorrow. So who, Catherine, I think this is one of yours. Would you like to say just a little bit?
Yeah, we just wanted to highlight that NASA is going to land the Perseverance rover on Mars tomorrow. Well, they're going to attempt to land it tomorrow, so we can all watch that. I think that's around 9 p.m. our time or so, a little beforehand. So make sure you check that out. There's actually 3 new missions at Mars this month. China and the United Arab Emirates have also just got some orbiters, and I think China has a lander on theirs as well. But anyway, so it's a very exciting time for Mars right now.
Excellent. Okay, so that comes to the end of our wonderful little game show that we've done here. So thank you all so much for taking part. Thank you for coming. We've just got one final thing that we'd like you to do, and I'm calling this Scientist of the Day. So I would like you at home to vote on who you think you want to win the title of Scientist of the Day. Now,
evil Scientist of the Day.
Evil Scientist of the Day, yes. So this could be the person that you thought had the most interesting facts, who was the most convincing liar, or maybe just who you thought was the most amusing. I don't know. It's up to you to decide.
Oh, you're not on there, Helena.
I haven't been presenting facts, so I
We wouldn't have done this without you.
You're my favourite scientist of the day.
Yeah, we'll vote for you.
Aw, thank you. That's too kind. Okay. And in the meantime, I can reveal that overall, you at home, as the audience, got 14 points. So that's out of 16. You only got 2 wrong. I mean, there are a couple that were very close margins, but congratulations, you did really, really well. So let me end the polling, and I can reveal that by, again, a very slim margin, the crown of Scientist of the Day goes to Helena Bates. So congratulations. I wonder why that is. Was that because you were good at lying, or I don't know?
She's got all those moon rocks.
I do. Well, I was going to say, come along next week and maybe you'll actually get to see some space rocks.
Yeah, exactly. Yes, so that leads quite nicely onto me just saying again, another huge thank you to everybody. Thank you for coming. Thank you, panelists, for taking part and being such good sports. I had fun. I thought that was very fun.
Thanks for hosting.
You're welcome.
Like somebody said that the Martian toy is the real winner.
Yes, Bruce the Martian. Yes. I still love the fact that you were trying to convince us that we'd taken a toy up to Mars and plonked it on the surface there, and there's just like a toy on the surface of Mars. I'd love for that to be true. I think that would be hilarious. Okay.
I mean, there are items on the moon that people left.
That is
yeah,
true.
isn't there like a golf ball on the moon?
Yeah.
But Alan Shepard, wasn't he like the first man to play golf on the moon?
Yeah, okay, so I've stopped sharing my PowerPoint now, and let's just do some questions. Okay. I didn't know if any of you happened to be having a look at them earlier, if there are any really interesting ones that you didn't get a chance to answer about any of your statements.
There was one that I wanted Burtie to answer, which was when would we actually be able to go to an exoplanet?
Good question.
Yeah. Are you going to write your whole lie up into a proposal?
Yeah, you should.
Send it off to NASA.
Maybe it's worth a shot. Yeah. I don't know. I'd say, just as a bit of a ballpark guess, maybe 50 years we could send a probe to an exoplanet. Yeah, if I just try and guess a number for it.
Is it one of
And
those
how long
things
would it-
like fusion technology, which is always like 30 years into the future?
Probably will work out that way. Yeah.
And
There's
how
a
long
lot
do
of
you think it would
technology we have to
actually
figure out.
take to get there? Like, it's not going to take 4 years, is it?
No.
Well, the idea of the light sail thing was to try and do it yeah, very close to the speed of light. So maybe that's the only way we could even do it in a sort of reasonable time frame, is to try and get something incredibly light, get it sped up to really close to the speed of light, and send it that way.
So is it about 4 light years away?
Yeah.
Okay, so that's where the 4 years came from. Nice.
Well, so we've had another exoplanet question. Can quickly answer. How are exoplanets formed?
So similar to how planets in our solar system are formed, so we have a protoplanetary disk, and you have the planetesimals colliding together and forming larger planetesimals, and they grow and grow until you have planets, and they can accrete atmospheres. So I mean, this is quite the nice thing about exoplanets is when you observe exoplanets, you're kind of observing almost every single possible way that planetary systems can form. With our own solar system, we can only see one possible formation scenario. When we look at exoplanets, we sort of see every single possible formation scenario that you could plausibly imagine. Quite a nice test bed for formation mechanisms.
Yeah, so much variety possible with exoplanets. Okay, quick question about one of those, the facts that we just did. Which country actually has had the most successful rocket launches? So I guess in terms of raw numbers, or percentages, I don't know. Do any of you know?
Off the top of my head, I don't know. In terms of percentages, I don't think anyone's ever will beat the UK in terms of having 100% success rate. I think rocket launches are generally sort of in the 60 to 70% success, any given rocket launch. That's the kind of level we're at.
Okay, so the rest of them are pretty all equal.
And I mean, there's a whole host of questions involved there about how you even define success as well. So it's difficult.
Yeah. We've got someone here asking, what are you currently working on? So maybe you could go around and just tell us a little bit about what you're currently doing.
Right now I'm doing this weird Would I Lie to You program.
Yeah, a bit odd, isn't it?
Yeah, that's what we're all currently working on. No, but what research will you be attempting to do tomorrow, let's say? Should we start with Helena? What are you up to at the moment?
So at the moment, I am classifying meteorites. So I am like at the end of last year, we cut a piece of rock really thin, so like less than the width of a hair, and we put it on like a glass slide, and we put that glass slide into a big microscope, which basically acts exactly the same as a microscope. So it uses so you know, with a microscope you use your eyes and you use light to look down at something very small, but instead of using wavelength of light, and here we use electrons, so you can get down to really small, so you can build up these beautiful maps of this really thin meteorite to like a really small scale. And then I use that information to basically work out what the meteorite is, give it a name, give it a classification. Yeah, so that's what I'm going to be doing tomorrow. More of that.
Cool. Catherine, what are you working on at the moment?
I am looking at some volcanic areas of the moon using remote sensing data. So data we get that's from the mission that Tris actually mentioned earlier, the Lunar Reconnaissance Orbiter. So basically I want to try to compare rocks that we have on Earth from different volcanoes to this mineral signatures, like the plot that I showed of what we see on the moon.
Not a crater.
So that we can, they're not craters, they're minerals, and to figure out what exactly those volcanoes are made out of. So that can tell us a bit about the moon's geologic history and how it was forming and how the surface features were all forming.
Awesome. Burtie, what are you up to at the moment?
So I'm working on the ground testing of an exoplanet mission called the Ariel mission. So I'm working on creating a light source, so essentially a fake star that we can use for ground testing, and specifically the thermal design so making sure we can get it to around, well, less than -200 degrees. So very cold.
Wow, nice. Okay, and finally, Tris, what are you currently working on at the moment?
A lot of my research is about looking at water on the moon and where it might exist. So I do a lot of taking data from missions and making temperature maps and then comparing them to models to see where you find very cold regions where water could exist. And also we try and combine kind of active water diffusion with the thermal models, so we can see water kind of hopping around the moon and how it might accumulate in certain areas.
Okay, so lots of different areas of research just in this one room, oh, virtual room, I suppose. Excellent. Okay, so a couple quick questions and then I think we'll just wrap up this. So someone's asked, how do you assign names to meteors? So how do we do that?
So it's actually really interesting how we assign names to meteors. So meteors are, you'll learn all about this next week, but meteors are actually the shooting stars. So they're not actually the meteorites, the bits of rock that survive. We name meteorites based on where they fall. So if somebody sees one fall and it's like in a town, so for example, in 1969, a meteorite fell in Barwell in Yorkshire and they called it Barwell, the Barwell meteorite. Then it's often named after the location it fell. But often meteorites are found, so people will go and look for a meteorite and they will then name it. And then it's named based on where it was found. And often it used to be named based on its nearest postcode. But now most of the meteorites are actually found in Antarctica. And Antarctica does not have any, it was named based on its proximity to its local post office. Antarctica doesn't have any post offices. So they've named various regions in Antarctica. So for example, we have the La Paz ice field, we have Grosvenor Hills, and then so the meteorite's named after that, and then given a number based on the year it was found and the number of how many meteorites were found that year. So unfortunately, I can't name any of them after myself, which I definitely would do, but I have to name them based on where they're found. So,
very imaginative.
What's a typical name then?
Well, so for example, so if you have a fall, we have meteorites that are called Nakla, which is a Martian meteorite. We have Murchison, which fell in Murchison in Australia. We have Barwell. We have Parnelly. We have Plainview. All very sort of like nice names.
Canyon Diablo.
Canyon Diablo, which is from Barringer Crater, which is awesome. But then we also have meteorites called LAP 02277 and GRO 95649. So they vary a lot. The classics, the absolutely unforgettable ones. So yeah.
Brilliant. Okay, another quick question. Back to exoplanets for you, Burtie. How many exoplanets are near our solar system? So I don't know how near is near, but sort of like how many would be near us?
Yeah, it all depends on what you count as near. In terms of what we could, well, the nearest one is orbiting around Proxima Centauri. So that's the one I talked about in my lie earlier. So it's about 4 light years away. If you mean near, as in within our galaxy, I meant there's typically around 1 exoplanet per star, and there are 10 to the 11 stars in the galaxy. Yeah, so a lot. Yeah, if you count near in the galaxy.
A lot. It's so hard to comprehend numbers that big, though. You just can't. So there's a lot of exoplanets. A lot of exoplanets. Okay, and on that note, I think we should wrap things up. Thank you very much, everybody, and thank you again, panelists. And hopefully see lots of you at next week's talk. So, bye-bye.
Bye.